Hello, everybody. Thanks for joining here. It's a pleasure that I can present my work here. So, I do quantum chemistry on the quantum computer. And since it's quite difficult to use those applications, I would like to give some overview about the computational methods, how to actually simulate quantum chemistry systems with a quantum computer. So first of all, I want to give a little outlook about what's possible within the NISQ era, so especially with respect to quantum chemistry applications. Then go also further into quantum chemistry itself, and give you some idea of what we want to calculate there, show you how to calculate this on the quantum computer with the variational quantum eigensolver, and then go further to the next step, so to go beyond this small hydrogen type of systems to simulate metal-organic frameworks on the quantum computer, and how we can do this with the current NISQ hardware. So let's first go to what NISQ era is about. You know those systems probably. Quite old computers. Well, they did their job, but well, are not that usable for quite a lot of stuff. And right now they evolved a lot, and we can do lots of things with our supercomputers now. Current supercomputers look similar to this system, but of course, the point is I want to show here is this system is basically in a stage that's far prior to this system. So even though it looks much more shiny, we still are in a very early stage of quantum computing. We do have lots of promising candidates for quantum computing, like NV centers, which were presented just in the talk beforewards, superconducting qubits, like that system here, ion traps, and lots of other ones. But all of them are in NISQ computers, so noisy intermediate scale quantum computers. They have short decoherence times, large gate errors, and few qubits. I put the point with few qubits into brackets because for our application this is not the critical issue. We have applications with very long circuits. I will show you a little bit more about that later. So our limiting part are decoherence times and gate errors. We don't care at the moment about having thousands of qubits. We are happy with having 10 good qubits. So just as a side note, why the few qubits are in brackets. So now all we want to have is quantum advantage. But let's look a little bit about what is quantum advantage and how far are we. Many vendors here promise everything. We can do quantum chemistry, optimization, all that kind of stuff on the quantum computer. And this slide is meant to show what we can actually do and what we intend to do, what's our vision, to distinguish that a little bit more. So we have some algorithms, like the Shor algorithm, which are theoretically proven to have some quantum advantage. So the Shor's algorithm is, as most of you might know, for prime number factorization used in cryptography, and it works nicely, is theoretically proven, and the only problem for application is upscaling the hardware, so to put it easily. Grover algorithm is also proven to have some quantum advantage, so those cases are quite nice and safe. Then we have also, for example, Google, who published a paper recently which showed quantum advantage in some practical case. But we should also keep practical in quotes, because it's just some kind of toy system which is nice for some very specific academic use cases. In this case, they could prove the quantum advantage. It's very nice to have it proven, but still, we are not at a point of practical quantum advantage. So that's the regime where we are in, trying to find the practical advantage. And there some applications like quantum chemistry, which I'm looking in, are very promising candidates. And I want to show you more details about how we go to the step of getting the practical quantum advantage, even within the NISQ era. So now I want to go a little step further to introduce a little bit about quantum chemistry to those of you who might not be that deep into it. So the idea of quantum chemistry is to solve Schrödinger's equation here, this little guy. It looks very harmless, but if you go deeper into it, we have some Hamiltonian, well, for example, that one. And in the end, we want to find the energy of the system. This is basically the foundation of all kind of material research you can base on. So this is the very basic principle of quantum chemistry. And with this Hamiltonian, it's so exactly this guy. It gets quite complicated with already very small systems. So you have a molecule with a couple of electrons, and then since they interact with each other, it gets very complicated to solve that on a classical computer very fast. So if you do it exactly, you get exponential scale up, and that's not feasible for larger systems. So the idea is to find an application to scale this up and calculate also larger molecules with higher accuracy. So we need to map the system on the quantum computer. So we rewrite all the stuff in a way that the quantum computer can understand it. This is done with Pauli strings. Pauli strings, here are different notations of it, are basically rotations around the Bloch sphere. So you have a qubit in the state 0 or 1, or some superposition, as seen in this Bloch sphere, and then some Pauli string rotates this qubit state. And we can rewrite the whole Hamiltonian of a quantum chemistry system of a molecule, in a sense that we have some Pauli strings of which this is composed. And we can then calculate the expectation value of these Pauli strings to get exactly this energy in the Schrödinger's equation. For that, the typical approach is a variational one, so variational quantum eigensolver. Here you see again the Pauli strings, and this is the expectation value of them. So we use some parametrized circuits, and then evaluate the expectation value on the quantum computer on this side, and then try to find the best set of parameters on the classical computer, get that set of parameters again, fetch it to the quantum computer, and with this loop we can iteratively go to the ground state of the system. This is a hybrid algorithm which merges the advantages of the classical and the quantum computer. So the classical computer uses the optimized optimization, and the quantum computer is therefore energy evaluation. So you can think of the quantum computer in that sense more of a QPU, quantum processing unit, similar to a GPU, so for a specific task. Then the question is basically how to parameterize these circuits for a practical sense. So there are lots of different so-called Ansätze for the circuit. Here in this example, you can see the hardware-efficient ansatz, which consists of some rotation layers, which are parameterized, and some entanglement layers. So entanglement is, as you know, the magic which makes the quantum computer superb to the classical computer. And with all this stuff, we repeated a couple of times. The hope is to represent the part of the Hilbert space in which the solution of the of this quantum chemistry system is. There are lots of different approaches to build this quantum circuit. This one is, as I told, the efficient SU2 ansatz. So it's made in a constructed in a way that it's very useful for the so that it's stirred to the quantum computer, very short circuit, so also usable for NISQ quantum computers. There are also other approaches like UCCSD, Unitary Coupled Clusters method, which is inspired by quantum chemistry itself, so the quantum chemistry which is usually performed on the classical computer, or which I'm investigating quite a lot, VHA, so variational Hamiltonian ansatz, which is based on the adiabatic theorem from solid-state physics. So all these ansätze have different advantages and disadvantages. Some are longer than others, some have more parameter to optimize, which make it more difficult to get the optimum, especially on some noisy NISQ quantum computer. So it's quite tricky to find the optimal ansatz, the optimal set of parameters, how to go on. Still, it is possible to find some results, even on the NISQ hardware. And I decided to show you here some results which are not post-processed much. So in the papers or all the merchandise, you can see all the nice graphs. Yes, we reached chemical accuracy and all that stuff. On purpose, I show you the raw data in the sense to see that you get a feeling what it means to have a NISQ device, and also to see the power of post-processing, of clever algorithms, of all that stuff, how far you can go with these noisy quantum computers, even if the raw results are not that nice. So here you can see some energy convergence. So this is exactly this iterative loop. You start at some quite bad energy value, and then the parameters are steered, and you get down further and further to some energy, which then in the end is hopefully the one, the ground state energy of the molecule. This is for a very small system, hydrogen molecule. So pretty much the smallest chemistry system you can imagine. And even for that system, we don't even reach the exact energy which we want. So even in this small case, it's not possible to get straight the exact ground state energy. One can also look at different mappings, for example, so to get the Pauli strings, and lots of other, let's say, meter parameters to stir. And with that, you can see, if you just do it naively on a kind of bad quantum computer, you get results which are just horrible. If you look closer into it, your results will get better and better. using some mappers which do some tricks called 2-qubit reduction, so you can get your system down from 4 qubits in this case to 2 qubits, have nicer results again. And one other important point is, well, if you look at the next generation systems, so here you can see quantum volume of 34 and here 128, even this relatively small step gives you much better results already, even if you use less of this, let's say, algorithmic tricks. So that's basically some figure which gives me hope that the development of next generation quantum computers will even further improve these results so that we can get better and better results. And, well, looks quite good already. Yeah. So you can see those are the results if you calculate it in a quite naive way. And depending on which parameters you tune, which mapper you use, which ansatz, you can go quite close to the exact energy which is here printed in gray. There are lots of algorithmic tricks or which can be found in different papers with which you can get even from these results something that's within chemical accuracy, so within some regime of 1.5 millihartz, which is basically the gold standard which we have from classical computing. That's also a little bit of a problem because classical computing is already very good with getting this chemical accuracy. So we have the problem that we don't need to find an okay solution. We need to be very accurate already. So quantum chemistry is quite hard to achieve on the quantum computer. Yeah. Now, with this background, I want to go further to larger systems. So all that you've seen till now is the hydrogen molecule, so the very smallest system. And you can see even that one has results which, well, make it difficult and to get nice results, but it's still possible. So algorithms can help quite a lot to go beyond the limitations of NISQ. So the next idea is to, go to quite large systems. Basically metal organic frameworks. Those are structures which have some metal centers and they are linked with some organic linkers, so just some carbon structures, and build large porous and periodic structures. These structures can then be used, for example, for CO2 capture or also to filter some certain molecules out of some gases. So in this case, it's filtering CO2 and nitrogen. And it's a nice application. So CO2 capture, I think I don't need to reason why we should look at it. So that's the system we have in mind for practical quantum chemistry applications, which are for interest also in industry in our society. But you've seen the previous slides. We were struggling with hydrogen molecule, and now that's a little bit larger than that. So I want to show you now how we can still reduce the difficulty of this system in a way that we can still calculate it on the current NISQ quantum computers. The basic idea of this algorithm is the active space selection. So in a large molecule, we have lots of orbitals with many electrons in it, but most of them are quite silent. They don't interact much with each other, and they can be easily treated with approximations like Hartree-Fock. And this is the inactive space and the virtual space. So orbitals which are just completely full or just completely empty and don't interact much with any of the others. And then there are also these orbitals in between within the active space. So there are highly coherent electrons interacting a lot with each other, and those are very tricky to treat on a classical computer. Those are the ones which make the computation on the classical computer hard and make the scaling exponential in worst case. So those are the ones which we are interested in. And the idea is, well, the quantum computer is good at hardware-Fock approximation. So let's just use the classical computer for the inactive space and the quantum computer for the active one. But now we need to ask how to find out the active space. So this is basically the chicken-egg problem. We need to know the molecule to find the active space. So it's a little bit tricky. But there's some workflow we implemented in our project. And this makes it easily possible. So we start with some unrestricted hardware-Fock calculation. So hardware-Fock neglects all these interactions between the electrons and is very fast and easy to implement on a classical computer. With that, we get a rough idea of how the molecule looks like. But this is still not good enough, so we do some Möller-Placid perturbation theory on that, which is also quite efficient on a classical computer. And also some other low accuracy methods to get the molecule in an approximate way. And as soon as we have the approximate solution of the molecule, we can select the active space based on the entropy of the orbitals. So entropy means in that sense that we look, is this orbital all the time just completely full or completely empty, or and then we aren't interested in it, or is it partly filled and interacts highly with other orbitals? Then we are interested in it and put it in the active orbital. And this is also done by the active space finder by our colleagues from HQS. So with this workflow, we can reduce our system basically from the whole huge molecule with lots of orbitals within, just to a very small subset of this active space, which we then can compute on the quantum computer. So you've seen the metal organic framework previously, and we cut off some of the parts of it, and so some clusters out of it. And here on the left you can see one cluster with a single cobalt atom in it, on the right side with two of them, and those are basically the molecules we now investigate. Do the whole workflow you've seen just in the last step, and then it basically looks like this. We start from the huge structure. Well, in this case it should be a cobalt MOF 74, just some detail. Cut out of it some smaller cluster, and then do the active space selection on this small cluster. So here you can see some example for this active space. This is the cobalt atom itself, and there are different orbitals, S and D orbitals, which are partly filled then. So the d orbitals would be added to the active space, while, for example, this 5s orbital, it's just empty and wouldn't be added. And with this approach, we can basically go down to system sizes effectively, which are in the size of hydrogen molecule or lithium hydride. So having like needing just 2 to 10 or 15 qubits, and with that we can then calculate it on the quantum computer. So we are able to reduce this huge system to just a very small system with a couple of qubits, a couple of orbitals, and then can calculate this on the quantum computer. And if you think of it, looking at the evolution of the quantum computers, within a relatively short time, we will then also be able to not use active spaces of 4 orbitals, but of 20 or whatever. So this whole approach can be scaled up. We directly parallel to what the quantum computer can give us. So the algorithm is there now. Now it's a matter of scaling up the hardware, and this is an approach to help make NISQ hardware usable already now. So I hope I could give you a small overview of how one can simulate even large systems on a quite faulty NISQ hardware, and thanks for your attention. Yes, sure.
In general, for quantum chemistry, what would be the properties of the molecule that you are looking for? Like if you simulate it, you will get some results, the ground state, right? What can you derive from that as a non-chemist?
Yeah. So the question was basically which properties can be derived from these calculations. So here in this case it was the ground state energy which we calculated, but you can also look at excited states. So this would give you properties like the infrared spectrum of a molecule, or just how it interacts with photons, so which light it can emit or absorb. Or also enthalpy of formation can be calculated with it. It would be just calculating the energy of one molecule, and then after a reaction, a chemical reaction, the energy of some products of it. And by comparing them, you can get the enthalpy of formation, and with that basically, if you do some chemical reaction, to say it like that, will it heat up or cool down? And those are some of the properties. And basically, there are lots of other properties you can calculate from that. Those are the ones which are maybe most intuitive. You're welcome.
That's when you perform these classical calculations to have these states which are always formulated. Do you also consider the geometry, or is the molecule, or is the geometry falling out of the simulation, or where does it come from?
Yeah, okay. So the question was about how to consider the geometry within the calculations. Let me maybe show the slide. In this case, we have some pre-optimized geometry which we did on the classical computer, but it's also using this quantum chemistry calculations. So maybe not the full CI, so those which are very costly, but some other ones. And I showed you the result of just the ground state energy of one single geometry. In the end, you can also calculate the gradient when you change the geometry slightly and build up a loop on top of that, so to also optimize the geometry with these calculations. So that's typically done on the classical computer. That's just some standard approach. It would also be possible to do that with our workflow. Okay. Yeah. So it's too silent.
Thank you. These 6 electrons in the active space, is that for the whole, the 6 electrons, is that for the whole, this whole cluster, or is it for each atom?
Do you mean here these numbers?
I was thinking about the slide at the end where you showed the, so is it 6 electrons that models this entire cluster? 6 active electrons in active space.
So in this case, we have, let's see, yeah, we have, it's just the same cluster here. So we have 3 electrons in the active space, so 6 spin orbitals. So it's basically just these 3 orbitals, and each orbital, due to spin up and spin down, results in 2 qubits on the quantum computer, and that would be the active space. Does that answer your question?
That's for the entire cluster, the middle picture.
For the entire cluster, I don't know exactly how many electrons it has.
I don't mean the left one, I mean the cluster that you take, this with 20 atoms or so.
So we can't hear.
Don't worry.
The question is, if those 6
Ins Mikrofon rein.
represent the whole COMOF 74 molecules.
Okay, I think I got the question. Thank you. Those molecules are part of this cobalt atom in there, but of course there are also more orbitals within the cobalt, so all of the, starting from 1s orbital to 2s, 3s, 3, and so on, so there are far more orbitals than just those which are seen here. Maybe that answers it, else we can just talk later.